Hello everyone. All right, well we are doing another YouTube Live. We do a YouTube Live every Thursday and Sunday at 9 p.m. Eastern Time. So it's good to see you here. Right now we are in a moment of transition where we're moving on to our courses. Just to give you guys some updates, we are still doing YouTube Lives every Thursday and Sunday at 9 p.m. Eastern Time. So please stop on by if you ever need any tutoring with any math problems. We are also going to be releasing the videos of our courses for statistics, so that will be out soon within the next couple days. And then we also have an ad coming up actually that's going to be pretty cool. It's going to show some students actually responding to some questions that I have for them. So this is going to be a really cool week for Amour learning, I believe. Now, there is a request from a student who is a subscriber. This is from Shaiju, and I just wanted to go over this with you guys. Let me real quickly fix a couple things, and then we'll be heading on over there. I'm going to transition into screen sharing with you guys so that you guys can see. All right, perfect. All right, so this is from Shaiju. He sent a list of 11 questions 2 weeks ago, and I want to be able to address all of these questions. So far we've addressed question number 7, which is the bottom question right there. I can't really seem to highlight that one. Explain the division algorithm. We do have a lecture for that. We also talked about this one, how to do modular arithmetic, for example, 75,769 mod 26. Today I want to go over, let's see, additive inverse and multiplicative inverse. Specifically additive inverse. And then if we have time, I want to talk about congruence relation and why congruence relations are important. So let's start with just what are congruence relations. So I personally don't like the name congruence relations because it's a little too fancy for me. When I say congruence relations, people get kind of nervous because the word congruence and relations, those are two kind of bigger words. To me, basically congruence relations is this. So I'm going to write congruence relations here. Now, congruence relations are actually pretty easy to understand if they're taught in a certain way. Here's how I like to think about it. What does equals mean? So equals just simply means that two things are the same thing. But also it's kind of like a scale. So if you think of it as like a balancing scale, where you have certain things on this side and certain things on this side. Equals just means that you can also add things on both sides and everything's still okay. So a couple things about congruence relations. First off, everything has to be equal to itself. So we're going to be fixed in a certain universe. Our universe is going to be a set S. It could be like the natural numbers or something that, but we're just going to say arbitrary set S. So that's the universe that we're going to be looking at. Basically, for all A in this set S, A equals A. Everything has to equal itself. That's basically all it says. So that's, if you want to be correct about the equal symbol and you have something that is not equal to itself, then there is a problem. It's no longer an equal symbol. It's something else. So for example, let me show you guys a symbol. And we're going to be working in the natural numbers. Or let's just work over the integers real quick. So this thing that you've seen right here, let me see here, this symbol right here, can this be thought of as an equal symbol? And the answer is no, simply because this is not true. 3 is not greater than 3. And if you think it is, then you're thinking of a different symbol than I am. But if this is the symbol that you're thinking of, greater than, that is definitely not an equal symbol, simply because the numbers are not equal to themselves, in the sense that this symbol you can't put the same number on both sides. Not only will that not always work, it'll actually never work, which is a lot worse too. So this is definitely not an equal symbol. So let me real quick erase this. There's a couple other rules about this congruence relation or equivalence relation. So a couple other things that need to be true. Let me think if I have this right. Yes, so if A equals B, this means that B equals A. Basically, this equal symbol, it should be thought of as a weight, but it's not like one side of the scale is different than the other side of the scale. So if we go back to our analogy with the scale, we have the scale. Basically, the idea is that if I swap both sides here, it should be basically the opposite picture. And so if I have two things that are actually balanced, and maybe they look different, it doesn't really matter. If I have two things that are actually balanced, and maybe I'll replace this one with purple, then I should be able to swap these two objects and it still is balanced. They still are actually equal. So that is required for any equivalence relation. So that's the second rule. And the third rule is a little bit more complex. It basically says if A equals B and B equals C, that means that A equals C. So to give you a sense of the balance again, I'm gonna try to draw what this looks like over here. So if I have, try that again. If I have two balances where I have a purple object over here and a green object over here, and these happen to be the same objects, and then over here I have two other objects. Actually, not two other objects, one extra object, the green object and the purple object, or another object, let's say blue. If this is the case, then I should be able to put either this blue there or this purple there. So either way. But let me just show you basically what this means. I can take a third scale and I can immediately know, so long as it's a congruence relation, I can know that if I put this here and this blue over here, that should be okay. So if these two are true, then this third one has to be true. So in order for there to be an equal symbol. That's really important to understand. Now let's go into the context of, we were working with last Sunday, I believe, we were working with mod 26. So mod 26, we have this universe, which is basically Z, and we have it split up into 26 different items. There's only 26 objects in this set. So 1, 2, 3, 4, 5, hold on, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. So there's 26. I basically split the integers into 26 pieces. And each group here has a label, like 0, for example, is one of these. Another one might be 1. And we go all the way up to the number 25. There's a 24 and everything in between. Let's try that again. Let's try this. Let's move that over here, 24. So we have all these numbers, and the idea is with the equivalence relation, if I have a number like 1, this in fact equals 27 mod 26. And why is that? Well, because if you remember last week or a couple weeks ago, if I divide 26 into 27, I get 1 with a remainder of 1. So these two are in fact equal to each other. But it also turns out that 1 is also equal to, let me see if I can get this right, 53 mod 26. So 1 equals 53 mod 26. Well, there's a lot that we can gain from this because we know that this equal symbol is in fact an equal symbol. And we can actually prove that. I'm not going to do that in this class, or in this lecture, sorry, but I would do that definitely in an abstract algebra class, which I should be posting within the next couple of years. But that's a long way to go. We got a lot. Well, it's actually in my number theory course, so you can check that out. And if you want a coupon code for that, here is the coupon code. This is KODYAMOUR. And just look up on Udemy, number theory. Just look on that course, number theory on Udemy, and you'll be able to get access to that. All right, so now we have these two pieces of information. We can actually show that 27 is in fact equal to 53. But why is this? Why can we show that based off of this information right here? Well, we have to be actually a little careful because here we have A equals B and we have A equals C. But that's not how the third rule was set up. It was set up as A equals B and B equals C, therefore A equals C. But we know by the second rule we can actually swap either one of these. So let's swap these two. This actually means that 53 equals 1 mod 26. So because 1 equals 27, or sorry, I should say because 53 equals 1 and 1 equals 27, that means that 53 equals 27. And that's by rule 3. And by rule 2, we can actually swap those if you need to. So it's important to understand that we can use those 3 rules to do this. Now let's, real quick, I'm going to check the live comments to see if we have any more comments. If you guys have any math questions, please feel free to post them over here. It's kind of hard to see, but it looks like we don't have any math questions, so I'm gonna keep moving. I have to pull it up again. I want to answer Shaiju's question regarding additive inverse. Multiplicative inverse is a little bit more complex, and I will need to talk about the extended Euclidean algorithm, but that'll be for another day. So I'll leave that for later. Additive inverses. So the add inverse. So we're going to work again mod 26. Doesn't really matter what universe you work in, so long as we're going to be working with mod 26. So what is an additive inverse? If you give me a number A, I need to be able to find something to add to A, something, so that I get 0. That is the definition of additive inverse. And the question is, what is that number? Well, let's get rid of mod 26 for a second. Let's just work with the integers. So if I have like 3, what can I add to 3 to get 0? What would go here? Well, my answer would be -3. And so 3 plus -3 equals 0. And so we can find an additive inverse for any number that you throw at me. So if you throw at me, let's say, -27, can I add something here so that I get a result of 0 in the natural number, or in the integers? And the answer is yes. The additive inverse is 27. -27 plus 27 is 0. So what about mod 26? Well, it turns out that -a actually works as well. So if you throw at me the number 23, my answer would be, the additive inverse to this would be -23. But the problem is, most people when we're working with mod 26, we're only going to be using numbers like 0, 1, 2, all the way up to 25. And -23, where is that on the list? And if I try to do like some division algorithm here in a negative 23, I never learned how to do this. So that's kind of weird. I need to find a way to somehow add a 23 to get to 0. And the answer is negative 23, but I need to figure out which of these numbers it is. And that's actually not too hard to figure out. There is a way of doing that. And so I'm going to show you how to do that right now. The cool thing is that if you give me any number, if we're working mod 26, so give me a number like 13. If I take 13, I can, this is actually the same thing as 13 plus 26 times any number, any integer k. Mod, now I'm going to explain this in a second here. Mod 26. This fact is true. If you take 13 and you add 26 or subtract 26, you actually still are, you kind of cycle through that mod 26 universe relatively quickly. Let me show you a pictorial model of this. If you remember, we thought of mod 26 as like this cycle. 0, 1, 2, all the way around to 25, and then back to 0. And each arrow represents what we do when we add the number 1. So if we're at 13 over here, let me try to make some room. So somewhere in between here, we might be at 13. Let's use a different color too. We're going to be at 13. Now, if I add 26, 26 would be 26 steps. I would actually be all the way back around, which is why 13 plus 26 is 13 still. So 13 actually equals, what's 13 plus 26? 39? So, and this is actually true. 13 equals 39 mod 26. And let's check that. If I divide 26 into 39, I should get a remainder of 13. This goes in once, minus 26, 3, 13. There's my remainder right there. So, so what I can always do is I can take a number and add 26 or subtract 26, and I'm not actually changing the number. I'm not changing the value of the number, so long as we're in this universe mod 26. This very weird universe. So that being said, now we can answer this additive inverse question, which is how do you find the additive inverse? Well, I gave you the answer, but we need to figure out what that number is. So let's work with green. So let's say we had 20, let's do 21. What's the additive inverse to 21? What number can I add here to get 0 mod 26? Well, the answer, like we said earlier, was just negative 21. But what is that number? What is negative 21? Well, we can take negative 21 and add 26, and we're actually still getting the same number. If we add 26, we're not changing the number. And this answer, by the way, is 5. So it turns out that negative 21 is the same number as 5. And we can actually check this. What is 21 plus 5? Well, it's 26. And 26 is divisible by 26. Therefore, we have no remainder. So this is how we can find additive inverses. Anyways, I'm going to go over one more time, go over the live chat, and then I'm going to go through a couple more announcements, and then we're going to move on. Yeah, we don't have anything in the live chat, so just understand, guys, if you guys have any questions, you can post everything over here. If you have any comments, questions, concerns, anything, just put your live chat over here. Make sure you hit the subscribe button if you haven't done so already. And share this with your friends. Tell them, like, hey, there's free math tutoring. And I'm sure they'd love to get some free help. So we have free tutoring every Thursday and Sunday at 9 p.m. Eastern time, which is right about now. This was a 20-minute session, so it's a little bit short, but that's okay. There's no problem with that. This will definitely get popular, especially when we start doing some advertising, and we have our future statistics course coming out in the next couple of days. So stay tuned for that, and hopefully by this Sunday, I'll be able to start announcing videos that are being posted regularly. So Have a good day, you guys, and I'll see you guys on Sunday, maybe even sooner. See ya.